Good morning. My name is Saundoji. I'm doing Masters of Statistics in the University of Wollongong. Today I'm going to present on the topic bounded influence regression. My presentation will be focused on least square regression, which is main part of bounded influence regression. My presentation outline, I'll focus on the bounded influence regression, least square regression, some mathematical formulas for least square estimators, and how to compute least square estimators and how to compute least square estimators in R, and with some conclusion and references. So what is bounded influence regression? Bounded influence regression is a robust regression technique which is used to evaluate the breakdown point of an estimator. By robust regression, we mean that any regression technique which is used when there are many outliers in the dataset, and it is used to overcome the influence of such extreme observations. The breakdown point of an estimator is the fraction of bad data that the estimator can tolerate without affecting it significantly. Bad data, I mean that the outliers or any set of data at the extreme end of the tail. To give example, for an example, mean has a breakdown point of 0 because we can change the mean value as much as we want by simply changing a single value of observation. Whereas the median has the breakdown point of 50% because more than 50% of the sample data should be changed arbitrarily in order to change the median. An estimator with high breakdown point is more robust than the one with the lower breakdown point because the higher breakdown point of an estimator has a low variance because the variance of the high breakdown point of an estimator are larger than the low breakdown point estimator. Therefore, the estimators with high breakdown point has a lower efficiency than the lower breakdown point estimators. Now, what is least square regression? Least square regression is a statistical technique which is used to estimate unknown parameters of a regression model and provide a robust alternative to the classical regression by minimizing the sum of squared residuals. Least square estimator has a breakdown point of 50%, which means that the half of the data can be influential in the ordinary least square regression case before we compute the LTS estimators. The least square estimator limits the influence of both outliers and leverage point by using only 50% of the data and completely ignoring the extreme outliers. So now, how to find the least squares estimator? The main objective of the least square regression is to determine the least square estimator, beta hat LTS, by minimizing the sum of smaller half of the squared residuals. So let us consider a regression model of a sample yi and xi with the response variable yi and the explanatory variable xi. Then the regression model yi is given by beta hat transpose xi plus arrow term epsilon I. Then the least square estimator for that model is given by the beta hat LTS, which is equals to arc mean sum of I goes to 1 from m r square I beta, where r square I beta represents the ith order squared residuals from smallest to largest among r1 square to r2 square to rn square, and the ri beta is calculated by yi minus beta hat transpose xi. And the m here is equals to n by 2 plus k plus 2 divided by 2, and these floor brackets indicates that we have to round it down to the next smallest integer. And the m is also called trimming constant. And the least square estimator can attain the maximum breakdown point when m is equals to n by 2 plus k plus 2 divided by 2. Although the least square estimator is easily described, but it's very difficult to mechanically compute least square estimator. In order to compute least square estimator, we have to fit the ordinary least square regression to all the subsets of the observations, and then finally find the estimator which minimizes the smaller half of the squared residuals. So in this case, the one approach recommended by Leroy and Rousseau in 1987 was to compute the least square estimator by considering all the subsets of size k plus 1 for which all the vector of the explanatory variables xi are distinct. So in this sense, the Leroy and Rousseau in 1987 initiated an approach to compute least square estimator by taking the subset which is equals to k plus 1 observations. So now, how to compute least square estimator? The following are the algorithm or the steps to find or compute least square estimators. In order to find least square estimator, first we have to determine all the subsets of n choose k plus 1 subsets of data. But according to Leroy and Rousseau in 1987, they focused on using k plus 1 subset of observations. Once we determine the subsets of data to use for the least square estimator, then we set up an initial values for the model parameters by usually using the ordinary least square method. And it is implemented in R using LM comment. And the next step is to calculate the squared residuals. Once we get the regression model using simple linear regression method, we find the squared residuals using the formula R squared is equals to yi minus beta hat transpose xi. And the next step is to sort the squared residuals from smallest to largest. We have to arrange in ascending order from smallest to largest all these squared residuals. And then next step is to remove n minus m fraction of observation of which the square residuals are large. In the way, we are eliminating the largest half of the squared residuals from the data. And then by using only the 50% of the smallest half of the squared residual, we minimize by using the least square method. And finally, we obtain the least square estimator, where the least square estimator is given by the one that minimizes this m equals to n plus 2 plus k plus 2 observations. So now, how to compute least square regression in R? So for example, in this case, I have taken the data from Duncan's occupational prestige data, and we want to see if there is any association of income and education with the prestige. In order to compute least square regression in R, first you have to install the package MAS, and then you call library MAS, and then use this command lqs and the formula of the regression and the name of data and the method we are using. In this case, we are using LTS. And in this example, our dependent variable is prestige, and the independent variables are income and education. And data, I have given the data name as data, and we are using the method LTS. And using this command, we get this output where the coefficients of intercept is minus 5.7643, and income is 0.8023, and education is 0.4098. And based on this data, Duncan's occupational prestige data, we found that the least square estimators are beta naught hat is equals to minus 5.7643, and beta 1 hat is 0.8023, and beta 2 hat is 0.4098. Therefore, the least squares regression for this model is given by prestige hat is equals to minus 5.7643 plus 0.8023 times income plus 0.4098 education. And this means that for a 1 unit change in income, the prestige will also increase by 0.8023 units, and when income remains constant and when we increase education by 0.1 unit, the prestige will increase by 0.4098 unit. And this is how we compute least square regression using R, using the library mass and this command LQS command. And we get the residual plot here, where we plotted the residual versus the fitted value prestige, and we found that the most of the residuals are bouncing across this zero line, which shows that our model is linear or more appropriate. And then it also shows that the residuals are very close to this zero line, which shows that the variance are constant, and so our model is fit. So now, what are the pros and cons of least squares regression? Least square estimation uses only 50% of the data that fits closest to the original ordinary least square regression line and completely ignores the extreme outliers. And thus, this method can misrepresent the trend in the data if it is characterized by the cluster of extreme cases or if the dataset is relatively small. So, the least square regression model gives best result or work very well when there is large dataset, but it gives poor results when we have small dataset. And these are the references I used for my presentation. Thank you.